So I wanted to give another numerical example here, how to calculate the probability that the London respondent gives a low score. So this is set up in exactly the same way as you've seen in the previous lecture. So what you do is set log of the probability over 1 minus the probability equal to the regression equation, and in this instance, by the regression equation we mean the fixed effects terms. So in this case, if you look at the fixed effects terms on the previous set of slides, you get the log of the probability over 1 minus probability equals to minus 3.082479. Take the exponential both sides. This gives you the odds ratio of the two probabilities, p over 1 minus p, equals the exponential of the regression equation, in this case 0.045845464. And then once you get to that bit, the probability can be calculated as 0.045845464 over 1 plus that, gives you in this case 0.044 to 3 decimal places. Okay, so it's a repetition of what you've seen before, and what you should hopefully see there is a certain knack as to how this works if you have to do this calculation. The probability is just the exponential of the regression equation over 1 plus that. So the second numerical example then, so some extra practice, but the main thing I wanted to try and get across here is this interpretation element, and consistent with the regression output we saw before, what you should see if you do this calculation is that this probability of giving a low score is lower for people from Scotland than from people from the London and Essex region. Okay, so there's an interpretation element to these things. It's not just a purely mechanical algebraic exercise. But in order to do the actual calculation, again, exactly it's the same way as you've done before. Log of the probability over 1 minus probability equal to the regression equation. In this case, because it's a generalized linear mixed model, equal to the fixed effects terms. In this case, this gives you log of the probability over 1 minus probability equals to minus 3.546173. Take the exponential both sides, so the thing on the right hand side should now be positive, and you now should have that p over 1 minus p is equal to 0.0288347779. There's a certain knack to this. The probability should now be the exponential of the regression equation over 1 plus that. So in this case, the probability is 0.0288347779 over 1 plus that. Okay, and there's a sanity check here, an interpretation element. This probability is lower for Scotland than for London. There was a final cross-check then. Recall that you've got 3 categories, so only need 2 regression equations to describe the whole system. What you can do in this instance is, as a cross-check, fit a generalized linear mixed model to estimate the probability of awarding a medium score. Technically, this should be a redundant step, so no new regional effects should be identified at this stage. So this is important here because there's some departure in terms of how you would think of this as just a purely mathematical exercise, and actually how you would think about this as an exercise in practical project work. So mathematically there shouldn't be anything here, so it's almost not worth fitting this model. Okay, but when you're doing this sort of things on a real project rather than just something that your lecturer has set for you, it's really a bit like being a detective, like Sherlock Holmes or Columbo, for example. So it's actually worthwhile to run this analysis anyway, even though you know mathematically you shouldn't technically identify any new regional effects at this stage. Okay, and I think this is sort of detective problem-solving element to try and emphasize for things like practical project work and for dissertations. So this thing, when it gets real, it's not just part of a university assessment. It's important to have these rigorous steps in mind when you do the analysis. So what we're going to do then is test for regional effects in the probability of awarding a medium score. So a lot of repetition here. Remember, R is like a robot. It will do exactly what you tell it to do, nothing more, nothing less. And once again, what you've got is this sort of familiar 2-step process. So the first step is a computational step, and then the second step is a summary step. So in the second step here, we've got summary of medium 2. Medium 2 is this generalized linear mixed model that we fitted in step 1. And the important thing to mention here is that the medium 2 name in step 2 has to match exactly the name mentioned in the first step. And our syntax for this computational step, step 1, the command used is glmmpql. This is the variable medium related to region. Then the random effects term is just a constant value for each individual product, i.e. hotel in this instance. Then you need the family equals binomial bit here to emphasize to R that this is a probability regression model, not a standard regression model. Okay, so you are calculating probabilities here, not just arbitrary measurements. Any probabilities that you calculate must therefore necessarily lie between 0 and 1. So again, there should be a lot of repetition here. So the main thing to focus on with these generalized linear mixed models are the fixed effects terms. And here what we've got is the table of t-statistics corresponding to these fixed effects terms. And similar to the previous examples that you've seen, where the action is on this table is the second row downwards. So what you would look for here is the p-value on the far right hand side of each row. Sometimes these are as presented below the name for each row. So for the London Essex region, the p-value is 0.1256. The North East Yorkshire region, the p-value is 0.5836, etc. Now the thing to watch for here is that none of these things are actually significant, because in each case either the p-values are bigger than 0.05 or the t-statistics are less than 2. So indeed, if you do these t-statistics calculations and perform the same analysis you've done before, what you see here is that there is no evidence here for any more regional effects. Okay, so this is tallying with what we said earlier. Okay, this is technically a redundant step. We shouldn't expect to find any more regional effects, and indeed we don't once we run this analysis. So in terms of the interpretation then, so we've got no evidence the p-values are all bigger than 0.05. Equivalently, the t-statistics are all less than 2 of a regional effect in this case. So consistent with the previous slides and our recognition that this was mathematically a redundant step, we find no evidence of any further regional effects. Now again, mathematically you could argue that this is a redundant step, but I think with practical projects and dissertations in mind, what's actually more important here is a sort of detective's way of thinking. It's a bit like being Sherlock Holmes or Columbo rather than Albert Einstein. Okay, it's worthwhile running these extra texts anyway, just to check. Okay, and then just to re-emphasize, when it comes to statistical work like this for things like dissertations and practical research work, though technically a redundant step, it's important to have these sorts of extra cross-checks. And once we've done these cross-checks and hopefully passed them, the implication is therefore we can be more confident that our early analysis is correct and we haven't made any obvious mistakes. Okay, and this continual sort of checking of your analysis at each stage is something to really emphasize when it comes to doing things like dissertation work and doctoral work beyond that. Okay, so another couple of numerical examples then. So you're asked here to calculate the probability the London respondent gives a medium score. So what you should see here is exactly the same way of working as in the previous lecture and in the earlier lecture examples for this lecture. So what you have to do is set log of the probability of a 1 minus a probability equal to the regression equation, and because this is a generalized linear mixed model, the regression equation just refers to the fixed effects terms. So once we've done this, what we have is that log of the probability of a 1 minus a probability is equal to minus 1.5554589. Take the exponential of both sides, so the odds ratio, the probability of or minus the probability is then equal to 0.211099249, i.e. just the exponential of the regression equation. And then the probability can be calculated as 0.211099249 over 1 plus that, i.e. the exponential of the regression equation over 1 plus the exponential of the regression equation. Okay, we get a value of 0.174 in this case. So there's an extra numerical example here, but again, the thing I really wanted to try and emphasize here is this sort of interpretation element, so that these things aren't calculated in a vacuum. What you're looking for here is a sort of sanity check. So in both cases here, the calculation for the London region and for the Scotland region gives you similar answers. So this is consistent with the previous analysis, which said there was no statistically significant evidence for differences between the London and Scotland regions here in this case. Okay, the rest of the numerical calculation works exactly the same as before. So set log of the probability of a 1 minus probability equals to the regression equation, which you get from the fixed effects terms. Here this gives you the log of the probability of 1 minus probability equals minus 1.7133827. Take the exponential both sides, so p over 1 minus p is equal to something positive here, 0.180255011, and then the probability can be calculated as the exponential of the regression term over 1 plus that. So in this case, this is 0.180255011 over 1 plus that, comes out at the end of 0.153. And again, the thing to watch for here is similar answers for both regions, reflecting no statistically significant evidence for differences between. So to summarise the lecture then, we've introduced linear mixed and generalised linear mixed models to account for correlation structures caused by the sampling frame and the method of data collection. So this might sound abstract, but this is a practical industrial problem, and indeed what could be argued to be a big data problem. This distinction between linear mixed and just linear models and generalized linear mixed and just general linear models is significant because it reflects in this case a delineation between a sort of student level of analysis and a professional level of analysis. Precisely the point here is to give a more robust treatment of previous estimates. It gives you more precision precisely because you account for correlation caused by repeat observations from the same product or hotel. Beyond this, mixed models are potentially very hard. Here the dataset can be criticised for its simplicity, that it does derive from a practical industrial problem. So this is quite a simple dataset, although far from trivial. The best thing about using R for big data is its online communities and freely downloadable packages. So I tried to give you a glimpse into the outside world here and how this really works. Here we've used LME4 package for linear mixed models and the MASS package for generalized linear mixed models. So as a reference then, this is the journal paper that we finally managed to get published 2 years ago now, which is forthcoming in Total Quality Management and Business Excellence. So it's finally published after a lot of hard work and some interesting stories about the revision process once the paper was submitted to a journal. Okay, so it's not necessarily a wonderful piece of academic work, but it is a practical industrial problem, and I think it's sort of useful to sort of see what you have to do in order to move on from a sort of student level of thinking and towards a professional standard analysis. Okay, some people wouldn't necessarily rate this as a wonderful academic journal, but we had to work very hard for the publication, and we were pleased that we finally managed to succeed in getting the thing published. And as I said before, I think it's useful to sort of see these things and how they are applied and formally published in their natural environment. It's not just the empty academic example just to sort of fill up a lecture slot.